Hello and welcome to the second part of our webinar series on flexible safety systems. My name is Thomas Frühwirth and I'm a research engineer at the Austrian Center for Digital Production. Today's topic is time-sensitive networking, and if you have not seen the first part of the webinar, I would recommend pausing this video, go back and watch the introduction and then continue here. You will find a link in the video description. We separated today's talk into three main topics, which are a recap of flexible safety systems and a mention of the three base technologies it builds upon. Second, and this is already the main part, I will briefly talk about time-sensitive networking, give a short introduction, discuss the supported traffic types, and also mention some additional features you may want to use in your industrial network. And finally, I will conclude the talk with a number of research topics we are currently working on. As you remember from the previous webinar, a reconfigurable manufacturing system aims to produce a large number of highly individualized products. This means that the manufacturing system has to be frequently reconfigured, which also affects the safety system. Hence, the need for a flexible safety system. Our concept of a flexible safety system builds upon three base and standardized technologies, which are time-sensitive networking, OPC-UA, and OPC-UA safety. The idea of time-sensitive networking is to bring real-time capabilities to Ethernet networks. It is simply a set of IEEE standards that allows you to build real-time applications on basic Ethernet networks. These standards are developed and continuously improved by the Time-Sensitive Networking Task Group. Now, a feature or a property that's often overlooked is that time-sensitive networking is a direct successor to audio-video bridging, or AVB. This means that all features of AVB are present also in time-sensitive networking. Thus, you can use time-sensitive networking hardware to transfer your video and audio streams, even if you don't need hard real-time guarantees. The key benefit of time-sensitive networking is its support for various traffic types, which are best effort traffic. Best effort traffic does not support any real-time guarantees, but you can use it for regular Ethernet traffic. The second traffic type is rate-constrained traffic, which is typically used to reserve a certain bandwidth in your Ethernet network. This bandwidth is then used for an audio or video stream, for example. And the third traffic class supported by time-sensitive networking is time-triggered traffic, which actually provides the hard real-time guarantees. For this to work, a time-sensitive networking interface has to support a number of features. First and foremost, these are different queues. A time-sensitive networking interface will support up to 8 different queues, and each of these queues can be assigned a different priority. These queues can then be used for different traffic types. The second main part is the gate control algorithm, which selects a packet from each queue to be transmitted next. And finally, the gate control algorithm builds upon the notion of a schedule in combination with a synchronized time. Thus, the main features that are required to implement the time-sensitive networking interface are clock synchronization, a traffic shaping algorithm implemented in the gate control list, and a means of configuration. Time-sensitive networking provides a number of additional features, like for instance reliability, which can be achieved by implementing redundant paths. This means that even if one link or a switch fails, you can still transmit your messages in real time over your Ethernet network. And another feature you may want to make use of is discovery. So whenever you plug in a new device into the network, this will be automatically discovered by the time-sensitive networking protocol. Now, to make time-sensitive networking usable for flexible safety systems, we need to combine it with OPC-UA and OPC-UA safety. And this is also the main research area we are currently working on. The example illustrated here tries to encode and transmit a signal via OPC-UA and TSN. The signal is provided by a sensor on the left-hand side and then encoded by the OPC-UA stack and transmitted via the time-sensitive network to the right-hand side where the actuator is located. To implement this, the end systems need to implement time-sensitive networking interfaces, which require the three different features I discussed before: clock synchronization, traffic shaping, and the means of configuration. To achieve minimum end-to-end latency, we need to somehow synchronize the OPC-UA application to the TSN network schedule, and this is another major research topic. And finally, the user or the application will try to configure new real-time communication links. So there is a need to configure communication links on both levels, the OPC level and the TSN level, simultaneously. This already concludes today's talk. Thank you very much for watching the second part of our webinar series on flexible safety systems. Visit us on social media like LinkedIn, Twitter or YouTube to learn more about the CDP, and stay tuned for upcoming videos. Have a nice day.